I need to try. I was wondering if you could send a picture of that roadmap you showed me and I've got you seen.
I emailed it to you.
Oh, you did?
Yeah.
Oh, it's because I checked right afterwards and I didn't see it.
Yeah, I didn't. I think I sent it around like maybe like 3:30.
Oh, you know what? That makes sense.
Yeah.
Okay, I'll check again.
Okay. If you didn't get it, just email me again. I can send it again.
Sounds good.
Yep. All right. It's 4 o'clock. Let's go and get started. All right. Good afternoon, everyone. How's everyone doing today? Good. Chugging along. I know we're almost there. One more lecture this week, and then next week's the last one. So almost there. Okay, so today my plan is to finish up these set of lecture notes on hypothesis testing. So we introduced the idea last time. We kind of got halfway through an example, so I do want to finish that up today. And then yeah, that's all I had planned for today. And so I was looking at the notes, and we may end early today. We may end early on Tuesday as well. But we are on track to finish up everything on time. Like I said on Tuesday, the final class session next Thursday, I'm planning to be just a finals review session. Okay. So I didn't get a chance to put out the final exam study guide just yet. Today just kind of ended up just being a bit busy with advising. But I plan on posting that tomorrow. Okay. So what I'm going to do is that after I post the final exam study guide tomorrow, I'm going to put a poll on Canvas for you guys to vote on which topics that you would most like to see on the final review session. Okay. Because we're not going to have time to cover absolutely everything. I am cutting quite a bit of content for the final exam, but it's still going to be quite a lot. And so I think for the final review session, we'll have time for maybe 2 topics for me to look at. Okay. 2 topics out of 4. So we have just first order ODEs, Laplace transform, Fourier transforms, and probability and stats. So I'll probably only be able to cover half of that stuff. And so I'll let you guys kind of vote and see which ones you'd most like to see in the review session. And then we'll cover that next Thursday. Okay. But plan for today is hypothesis testing. Plan for Tuesday is going to be regression analysis. And so that has to do with the very last problem on your homework. And then final review. And then we're wrapping it up. Okay. So our final exam for this class is going to be the Tuesday of finals week. So that's Tuesday, May 12th, I believe. It's going to be 5 p.m. until 7 p.m. essentially in this room. Okay. So it is a bit early in the week. But that also means that gives me a chance to grade the final exams early as well. So you guys I should have the final exams graded and back to you guys before the end of finals week. That is my plan. Okay.
You say back to us, that's if we come to pick it up.
Yes. Yeah. So I would say, very few people come to pick up their final. But the grades will be on campus before the end of the week. And then if you want to have your final, I'll have it in my office. Yeah. All right, so that's the plan moving forward. Any questions I can answer before we get started for today? Okay, good. All right, so let's go ahead and pick up where we left off. So actually, I'm just going to scroll up for a second, just because, last thing that we covered on Tuesday was just the whole methodology for hypothesis testing. So we actually got through all 6 steps. So before we kind of continue on with the example, I just want to kind of run through them really quickly again. Okay, so you should have this already written in your notes, and so I'm not going to, I'm going to go fairly fast. But this is just to kind of start the conversation today and just get a refresher. Okay, so the whole idea with hypothesis testing is to give us a systematic way or a standardized way to test a hypothesis. Okay, because generally what's going to happen a lot, in your engineering careers is that you're going to be forming hypotheses. Whether you like it or not. And so, it's not going to be as, it may not be in a formal scientific lab setting, but there will always be situations where you're going to estimate the value of a parameter. You're going to estimate the value of some kind of property of material, and you need to perform tests to verify that value. Okay. So this is kind of the standardized steps that you would take in order to test that hypothesis. Okay. All right, so step 1 is to form your hypothesis, right? So you can't test a hypothesis without forming one. So usually this takes the form of some kind of equality statement. So you're going to hypothesize that the value of some parameter, the value of some variable is equal to some certain value, okay? So if you recall for this example right here, we're looking at the structural strength of some wire that we're purchasing from a vendor, okay? And what the vendor is claiming is that their wire can sustain up to 200 pounds of force before they break, okay? And so we want to test that before we actually put that in practice, because that's generally a good idea, right? So it's you don't just trust vendors blindly, you have to kind of verify it yourself. Okay, step 2. So step 2 is to form what's called the alternative hypothesis, okay? So the alternative hypothesis, the name is a little bit misleading, and so it's called the alternative, but I like to kind of refer to this as the rejection criteria. Okay, so it's the criteria with which we're going to use that we're going to determine whether we're going to reject our original hypothesis. Okay, now your alternative can take a few forms, and so that's something we're going to cover later today. But usually the alternative is some kind of inequality statement, okay? And you have to use a little bit of ingenuity with your alternative, because you have to think about, given your situation, given the kind of the context of which you're testing this hypothesis, what is the scenario which is going to cause you to basically change your decision, right? So for our example here, we're testing the structural strength of these wires, right? We want these wires to sustain at least 200 pounds of force. And so our alternative hypothesis for this particular example is if we find out that that's less than 200 pounds, then we're going to reject our hypothesis and purchase a different one, okay? Now, a different alternative, an alternative, I guess you can say, is let's say that we do our test and we find that the breaking limit is greater than 200. So technically, in that case, then our original hypothesis would still be false, right? We find that the breaking limit was not 200, it was greater than that. But, in that situation, we're not exactly mad at that, because we could still use it for our application, okay? So for the case where we find that the breaking limit is greater than that, we still accept our hypothesis, okay? Right, and so for this particular problem, our alternative is mu is less than 200 pounds, okay? Okay, step 3. So once you have your alternative hypothesis, you have to specify what we call a significance level, okay? Now, the significance level is kind of an admission that, even if you're going to be performing these tests, even though you're going to be performing these measurements, there's always a small percentage chance, a small probability that, your tests are not representative of the true nature of, whatever you're testing, okay? Because testing is limited, right? And so it's impossible for you to test to do an infinite number of examples. And so there's always a chance that, maybe you just got a bunch of bad samples, or maybe your testing was just a little bit over optimistic. And so you always have to kind of factor in a little bit of uncertainty in your calculations, or uncertainty in your decisions, okay? So that is defined as your significance level, right? So usually you define this as some kind of low number. So you don't want to set a high number that you're going to be wrong. So something like 5% or 1% is usually pretty common for this significance level, okay? Okay. Step 4 is to use the t distribution to compute the value of c from the table, okay? So that's the part we're going to go over today as well. So you're also going to need the t distribution for your homework problems on confidence intervals as well. Okay, so we'll go over how to do that. And the way that you're going to do that is you're going to use a certain value for f of c. So you're going to either set f of c equal to alpha or 1 minus alpha, depending on your application. Okay. And then to use the table, you're also going to need the degrees of freedom n minus 1. Okay, so that's one thing that we'll go over today. Okay. Step 5 is once you've kind of done all this kind of pre-work, or kind of the preparatory work, now is the time to actually do the experiment. And so this is when you're going to do your test, take your measurements. This is when you're going to compute your sample mean and your sample variance. Okay. Then you're going to use this formula down here to test whether you're going to accept or reject your hypothesis. Okay. So you're going to compute t is equal to x bar, the sample mean, minus mu, which is the hypothesized value. Okay. Divided by S, where S has the same definition as before. S is the sample standard deviation. Okay. And N is the number of samples. Okay. So depending on what you receive from S here, or excuse me, depending on what you compute from T, you're going to compare that from what you found from C from the table. And depending on their relative values, you're going to accept or reject your hypothesis. Okay. Okay, so that is kind of the 6-step process to hypothesis testing. So let's go ahead and apply this process here. We've already kind of done it a little bit, but let's kind of fill in all the details for the example that we were going over last. Okay. Okay. So let's do example. Okay. Okay, so we're going to test the structural strength of a wire using the methodology for hypothesis testing. Okay. All right, so let's go through all 6 steps again, just kind of from the top here, just so kind of we're all on the same page. Step 1, state your hypothesis. Okay. So in this case, our hypothesis is basically we're going to be testing the vendor's claim, right? So the vendor's claim in this case is that the breaking point is 200 pounds, right? Or in other words, the wires can withstand at least 200 pounds of force before they break. Okay. Okay. Step 2, after we have our hypothesis, is to form our alternative. Okay. So remember, when you form your alternative, you're going to need to use a little bit of ingenuity to determine, whether, which side you go, which side you're on. Okay. So in this case, since our design will fail, if the breaking point is less than 200, right? So let's say we're using this wire for some kind of application which requires them to hold at least 200. Okay. That means our alternative is mu less than 200. Okay. All right. So for an alternative like this, where basically what we're saying is that if we find out that our breaking point is significantly less than our hypothesized value, right? We call this a left-sided alternative. Okay. Right, because our rejection, you can say our rejection region is on the left, right? And so if what we measure is on the left of our hypothesized value, then we reject it. Okay. There's also a right-sided alternative and also a two-sided alternative that we'll go over later. But I just wanted to find that right. Okay. Okay, step three. Step three is to choose a significance level. Okay. So our significance level, that is you can think of that as the amount of uncertainty that we're going to expect, right? And so this is usually some kind of low number. So let's say that alpha in this case is going to be 5% or 0.05. Okay. Now, step 4. So this is the part that I think it gets a little bit confusing. Okay. So step 4, now that we've established this information, we've established our alternative and the significance level. Step 4 is to actually choose, first of all, choose a random variable to model our uncertainty. So you have two options here, and the two options are exactly the same as the two options for confidence interval. So either you're in a case where you know the variance beforehand, okay, or you're in a situation where your variance is unknown, and so it's something you're going to determine from the data. Okay. So in the vast majority of cases, you're going to be on the right side of this diagram here. You're going to be working in a case with unknown variance, because most of the time, if you know the variance beforehand, there's most of the time in those cases, there's not that much reason to run an experiment because you already kind of know what the variance is. You probably already know what the expected value is. So most of the time when you're going to go through the trouble of running an experiment is because you don't know the variance. Okay, so most of the time you're going to be on the right here. And so in these situations where you don't know the variance, you're going to use what's called the t distribution to choose the random as your random variable. Okay, so the t distribution is a type of random variable. It's similar to the Gaussian, but not quite. Okay. All right, and so we've actually used this already. So if you think back to our lecture on confidence intervals, there was a point where we were working with the case with unknown variances, and I told you to look up the values in a particular table in the textbook. Okay. Now I realize that not everyone has the textbook, so I do have this table posted online for you. Okay. Okay. But then the issue now is, how are we going to use it? Okay. So to use this, right, very similar to our confidence intervals that we went over before, we need to compute something called f of c, which is going to help us look into a particular row in the table. Okay. Okay. So for a left-sided alternative, okay, for a left-sided alternative, the value for f of c here is actually going to be exactly alpha. Okay. All right, which in this case is 0.05. Okay. So we need that piece of information to look up in the table. We also need to know the number of degrees of freedom. Okay. So the degrees of freedom for any given problem here is n-1, where n is the number of tests that you're going to do. Okay. So for this particular example, I haven't mentioned it just yet, but let's say that, before we purchase a large amount of this wire, the vendor has sent us 25 samples for us to test. Okay. So for this example, it just happens to be 25. But of course, that number is going to be different depending on your situation. Okay. So if we're running 25 tests, that means our degrees of freedom here is 24. Okay. Okay. So keep those two pieces of information in mind. And so, for you guys, you can just keep it in front of you. But let me open up the T distribution table just so that you can kind of take a look and see what it looks like. Okay. So if you look on week 15 of the Canvas site, you'll see that I've posted a new file at the bottom. Okay. And that file is called the T distribution table. Okay. Okay. So that file is here, right? And so if you actually look at the top of the file, this is the table of Laplace transforms. The reason for that is this is a sheet I'm going to provide you on the final exam. Okay. So it's going to have the Laplace transforms because you need it, but we don't need it for now. Okay. But what we need it for is this part right here, which is the table of T distribution. Okay. Okay. So the way to unfortunately I can't edit it right now. Let me see. Oh, here we go. Okay. Okay, so the way to use this table is we're gonna first look at the rows, right? So the rows are gonna correspond to the value for f of c. Okay. So they call it f of z in this table, but f of z is the same thing. Okay. So first we're gonna look up the row in terms of what our f of c value was. Okay. And then we're gonna look at the column based on the number of degrees of freedom that we have. Okay. Okay. So this table actually it keeps progressing from left to right. It's just that the table, the page is limited. And so these tables down here are exactly the same thing. Okay. All right. So for our example that we're working just now, we know our degrees of freedom. So our degrees of freedom was 24. Okay. Okay. So we're going to be looking in that column right there. And we know that our f of c is 0.05. Okay. Because we had a 5% significance. Okay. Okay. So we need to find the row for 0.05. But we don't have that here, right? And so the table only goes up to 0.5 for f of c. Okay. All right. So what are we going to do? Okay. So luckily for us, the f of c table is actually symmetric. Okay. And so the reason we don't go down to 0.05 is that we can look at the reciprocal value. And so the reciprocal value actually corresponds to this row right here. Okay. Or 0.95, because if you look at 0.95, that's equal to 1 minus alpha, right? Or if alpha here is 0.05, that means 1 minus alpha is 0.95. Okay. Okay, so for a left-sided hypothesis, you do have to make use of this kind of reciprocal property of the table. Okay, so because the table is not going to go all the way down to 0.05 or 0.01 or 0.1, right? You're going to have to look at the opposite side. Okay, and so you can see where these two things intersect, right? And so you can see that they intersect at a value of 1.71. Okay, so that tells us our C should be 1.71. Okay. But, so this is for an f of c of 0.95, right? And so since we're not actually looking at our special value of significance here, we're looking at 1 minus significance, we actually need to invert this, okay? So instead of 1.71, our value of C is actually going to be negative 1.7, okay? And the negative is because, we had to look on the other side of the table, okay? Okay. I know that was kind of a lot, and so I'll go back to the the whiteboard and kind of summarize that there. But that's kind of the idea. So to use this table for a left-sided alternative, you look at 1 minus alpha, you look up that value in the table, then you multiply by -1. Okay. The easy way to remember, just because I know that's not a step, is that when you're doing a left-sided alternative, your C value should always be negative in that case.
When you're saying left side alternative, is that just basically saying the lowest outliers that are acceptable?
Yes, exactly. Yeah. So when your alternative has a less than sign, then that's a left side. Yeah. Okay. All right. I'll go back and kind of summarize this all here. But any questions on this so far? Okay. Okay. So let me go ahead and we should just be able to exit here. Okay, so that's the table. So that's posted for you on Canvas here. Okay. So for left-sided alternative, right? So step one, or we've already used the numbers. So let's say step A is going to be set f of C to 1 minus alpha. Okay. B, look up the corresponding value in the table. Okay. Right, so you're going to look up the corresponding value for 1 minus alpha, not just alpha. Okay. And then C, you're going to multiply it by -1. And so in the end, right? So for a left-sided alternative, the value of C that you're going to end up using is actually going to be a negative number. So that's one way to kind of check and just kind of sanity check your way out of it. Okay. Okay. All right, so that's step 4 right there. And so, from this, we obtained, for this particular example, for the number of samples that we have and our significance level, our C here is going to be -1.71. Okay, good. All right, so that is step 4, right? So step 4 is to look up the information in the table based on your random variable, right? Step 5 is to actually run your tests and take measurements. Okay. Okay. So unfortunately, I don't have wires for you guys to test in here. You're just gonna have to trust me that I ran these tests. Although in this case I didn't. I just made up these numbers. And so let's say we ran the test and we got a mean value, sample mean of 197 pounds. Okay. So slightly below, right? So not as high as the 200 pounds that the manufacturer claimed, but maybe this is close enough, right? So we have to see whether this difference of 3 pounds is significant enough for us to actually reject our hypothesis. Okay. And so let's say that we have a sample variance. We found the sample variance to be 36 pounds. Okay. And so that means if our sample variance is 36, our sample standard deviation is a square root of that, which is 6 pounds. Okay. And I apologize. So the sample variance should be 36 pounds squared because it's units squared. Okay. So normally step 5 is the fun part. That's when you actually get to do the tests. But I just kind of took all the fun out of it. I just gave you the data. And then step 6 now is going to be to decide whether we're going to accept or reject our hypothesis. Okay. And so to do that, we're going to compute a value t, right? So this is the last formula we went over last Tuesday. And so t here is going to be x bar, which is our sample mean, minus mu, our hypothesized value, divided by s, our sample standard deviation, divided by square root of n, okay, number of samples. All right, so let's go ahead and plug everything in for this since we have everything here, right? So our sample mean in this case is 197, so we're going to plug that in for x bar. The hypothesized value, remember this was the value that was given to us by the vendor, so our hypothesized value is 200 pounds, okay? The sample standard deviation S, we have already determined that from our data, so that's going to be 6 pounds. And then N, right? So N here is the number of samples that we did, which was 25 pounds.
You might have mentioned it, but what's the significance of subtracting the degree of freedom and having 24 and then using 25 right there?
Yeah. So the degrees of freedom, that's just based on how the distribution is defined. And so if you remember, when we compute sample variance, right, we have the 1 over n minus 1. And so that n minus 1 is to account for the fact that, when you compute variance, you're computing differences between different variables. And so for 25 variables there's 24 differences, if that kind of makes sense.
So the space.
Exactly. Yeah. And so the t distribution is kind of defined the same way. That's why degrees of freedom is n minus 1. Yeah. Great question. Okay. All right, so let's go ahead and plug all those in, but for this value here, we compute the sample, so this is the number of tests that we actually make. Okay, so we plug everything in here, and what we get is a minus 2.5. Okay. Okay. Now, we got our values here. So this minus 2.5, you can think of this as the result of our testing. And so it's negative, right? So it's negative to reflect the fact that, what we obtained from our tests was lower than what we hypothesized. But is it low enough, right? So is it low enough? Is our measurements low enough such that we can reject our original hypothesis? Okay. So the way we determine that is that we compare this to the value of C that we obtained from our distribution. Okay. Okay. So we're basically going to compare the value of C versus the value of T that we computed from our experiment. Okay. So C, you can think of this as the theoretical kind of variance that we should obtain from our data. Maybe variance is not a good word. Theoretical, I would say deviance from the data. or deviance from our hypothesized value. Okay. And this t here is the actual deviance that we found. Okay. Okay. And so we're going to compare their values, compare to our alternative hypothesis, and use that to determine whether we're going to accept or reject. Okay. All right. So if we fill in these values, right? So the theoretical deviance C is minus 1.71. Okay. And our actual deviance is minus 2.5. Okay. All right. And so since our actual deviance here is more negative, right, we can say that our actual deviance is greater than our theoretical deviance. Okay. Okay. And if we take this information and we relate it back to our alternative hypothesis, right? Remember, our alternative hypothesis is if mu is less than 200 pounds, right? And so since our actual deviance is greater, and since that falls within the alternative hypothesis, right? And so kind of the other definition for alternative is that if your alternative is true, then you reject your original hypothesis, okay? So since our alternative is true in this case, the actual deviance that we found is greater than what we can theoretically accept, then in this case, we are going to reject our original hypothesis. All right. So in this unit here, it's very easy to get into like double, triple negatives and to kind of like trick yourself into saying the wrong answer. So let me kind of just write it out in words again. Okay. Since we found, or since I should say, since our test found that the actual breaking point is significantly less than the hypothesized value, okay? So that's established, right? And so that's we found that the breaking point was 197, which is not that much, right? So it's only a 3-pound difference, but it is enough, right? And it's enough because we compared it to the theoretical deviance that we should have gotten. Right? Then we're going to reject our hypothesis. Okay. Right. So that's the conclusion that we draw kind of in words from this test. Okay. All right.
Can you relate the magnitude to the alternative one more time? Just to
Sure.
bridge the gap between those.
Exactly. So basically, you know, we found our measured breaking point or the mean to be 197, right?
Yeah.
And so what we want to say is that, okay, this is less than what we wanted, right? We wanted the breaking point to be 200, but is that difference of 3, is that significant enough for us to reject our hypothesis, right? Because what we're saying is that, you know, we're only doing 25 tests, right? Right? And so it could be that, you know, among those 25 tests, there's just always going to be some random variance in there. Maybe we are, you know, maybe the variance of what we computed is not that bad, right? And so let's say that instead of 197, right? Let's say that our mean was actually 199, right? So we're only 1 pound less. And so that is technically less than what we hypothesized to be, because we hypothesized it to be 200, right? But, you know, given the fact that we're only doing a finite number of tests, right? It's possible that there is going to be some random fluctuation. And if that random fluctuation is enough to be captured by our random variable, right? So that's kind of what this quantity says right here, right? So this C value here accounts for the fact that there's going to be some random fluctuations anyway, right? And so if that kind of deviance from 200 to 199, if that can be explained by this random deviance, then we can say we can still accept our hypothesis because it's close enough, right? But what we're saying now is that, you know, because the difference was 3 pounds, so from 200 to 197, this is significantly less than what we had hypothesized.
So the C value, to use a bell curve for ease of understanding, the C value essentially creates your wall on the left-hand side.
Exactly.
If you pass that wall towards the negative, this one went more negative, it fails the test automatically.
Exactly.
How to accept your alternative.
Exactly. I think that's actually a great way to put it. So actually, let me draw that out because I think that'll make it a bit more clear. And so, you know, so what Anthony was saying is that, you know, for any kind of given random variable, right? We're going to assume that the deviance is going to be on a bell curve like this, where, you know, the peak of the bell curve, this is our hypothesized value. Right? And so what we're computing with the C value, we're computing basically the left bound of this, right? And so C, you can kind of think as kind of this distance right here. Okay. Right. So the C kind of sets a lower limit in terms of what you're willing to accept for the value and still accept your hypothesis. Okay. So what we found from these tests was that, you know, from our measurements, our T value was actually out here. Right. So it's on the lower end of that bell curve, away from the peak. And so because it's further away from the peak than what we can accept, we can say we reject our hypothesis. Okay. Okay. Yeah, this is a good example.
And then if the T value is equal to C or above the C, that's where that uncertainty of error on your part comes in. Say it's probably my mistake, but it meets our standards.
Exactly. Exactly. Yeah. So for the case where, you know, let's say we measured a 199 for the breaking point, that's probably going to be around maybe like right here. Right. And so technically that's less than your hypothesized value, but, you know, it's within parameters. It's within uncertainty to say that, you know, it's the true breaking point is probably still 200. It's just that maybe just the samples that we got were, you know, not as strong of a sample size. Yeah. We could be on the other end as well. So let's say that, you know, let's say we measured the breaking point to be 205. And so that's over here, right? So technically that's far off from our hypothesized value as well. But based on our alternative, we can say we'll still accept this because we can still use it for our application. Exactly. Yeah. Mm-hmm. Cool. Right. Any other questions on this example here? Okay. All right. So with that said, let's dive into alternatives a bit more. In particular, let's talk about the different types of alternatives you can do and their corresponding rejection regions. Okay. So the example that we did was a left-sided alternative, right? And so for a left-sided alternative, what we're saying is that if our measured value was significantly less than our hypothesized value, then we reject our original hypothesis, right? And so if mu x bar is significantly less than mu, okay, then we reject, okay? So if you were to draw this out, although technically, you know, we kind of drew this out already here, right? But traditionally, the way that the rejection region is formed is that it's formed on a number line like this, where in the middle we have our hypothesized value, okay? And so when you compute C, right? So C right here kind of falls on the left side because it's negative. So what we're saying is that everything to the left of this, right? Right, we call this our rejection region because everything, if our value of T is less than C, then we're going to reject our original hypothesis. Okay. So for a left-sided alternative, kind of what we discussed before, your f of C that you're going to use to compute the values from the table is just alpha. Okay. Now, because of the tables that we're working with, you know, the ones that I've given you, you do have to do kind of the reversal trick. So you have to kind of set this to, you know, 1 minus alpha, then invert, right? So if you had a more full table, so if your table for the t distribution went all the way down to 0.1 to 0.5, 0.05, then you could do that. But because of the table that I've given you, just because I don't want to kill too many trees for you guys' exams, we have kind of a limited table. We have to use this one. Okay. Okay. All right. So then let's now define the right-sided alternative. Okay. So the right-sided alternative is the opposite. So the right-sided alternative means that we're going to reject our hypothesis if our measured value is significantly greater than our hypothesized value. So in that case, our C value is going to be positive. And where we reject is everything to the right of this. Okay. All right, and so for a right-sided alternative, the f of C that we're going to be using is 1 minus alpha. Okay. And so in this case, there's no need to invert it or multiply by -1. We can just use the value just kind of straight up, just like this. Okay, so you're going to end up with a positive C, and that's exactly what you expect. Okay. Right. So I would say, for the majority of cases, in engineering, you're either going to be working with the left-sided or a right-sided alternative, right? There's usually a good reason to pick one or the other. It is possible to have a two-sided alternative where you're going to reject both on the left and the right. Right. And so in this case, we're saying that our hypothesized value should be equal to our measured value should be equal to our hypothesized value. Okay. So we're going to reject if we're too low, and we're going to reject if we're too high. Okay. So that means the rejection region is going to be on both sides. And so we have our hypothesized value mu. Okay. On the right, we're going to have a rejection region just like before. Okay. And we're going to have a rejection region on the left as well. Right, so we're only going to accept our hypothesis if we're in that kind of narrow band right around our hypothesized value. Okay. And so for two-sided alternatives, you do have to do it twice. So you have to solve for two C values. Okay. All right, so you're gonna have f of C1 is equal to, and f of C2. Okay. So you have one for the left side, one for the right side. Now, what's interesting about this is that, we're not just going to use our significance level by itself anymore, right? So in this case, the significance is actually going to be split. So half of the significance is going to be split on the left side, half of it is going to be split on the right side, okay? Okay, so that means f of C1. So C1 is going to be for the left-sided alternative. This is going to be alpha divided by 2. And then f of C2 is going to be 1 minus alpha divided by 2. So be careful of that. So when you do the two-sided alternative, make sure you have the significance. So half is going to be on the left, the other half is going to be on the right. Okay. Okay. So next example we're actually going to do a two-sided alternative just so that you can kind of see. Okay. All right. Any questions before we jump into that example? Yes.
Will we get a negative? I know you said it will be positive, but would we get a negative number in any circumstance for the right-sided?
No. So the right-sided, your C value should always be positive. It has to be to the right of your hypothesis. So, yeah.
I'm just thinking back to the example where we did 1 minus.
So we did 1 minus that, but then we multiplied by -1. So everything in the table that I'm giving you guys for the exams have all positive numbers, but just know that you have to multiply by -1 because you should get a negative for the left side. Yeah. Mm-hmm.
That was just
Right. Mm-hmm. Right. Any other questions before we jump into an example? Okay. All right. So this one's going to be a little bit more of a contrived example, so not really a physical problem. But we're just going to look at a theoretical random number. Okay. All right. So let's say we're going to have a variable x. It's going to be a variable with a known variance. Okay. So this is a little bit unusual. So remember, most of the time you don't know the variance beforehand. But I did want to give you one example of this just so that you can kind of see what it would look like. Okay. All right. So let's say that the known variance for this variable is going to be 9. Okay. Okay. So the hypothesized value for x is going to be 24 in this case. Okay. So that right there is going to be our mu value. That's our hypothesized value. All right. And then let's just also assume that we're going to run an experiment where we're going to measure the value of x 10 different times. So we're going to take 10 samples. So 10 right there is a number of samples n. That means our degrees of freedom is also going to be 9. Okay. Okay. So based on this information, we need to determine the upper and lower bounds for our mean for us to accept our hypothesis under a two-sided alternative. So under a two-sided alternative, So this example is a little bit unique because we haven't run the test yet. So we're going to run the test after this. But based on what we know from the problem beforehand, we can determine, what our measured value should be in order for us to accept our hypothesis. Okay. Right. So this is quite common as well. So in that case, this problem is actually a little bit similar to our confidence interval problems as well, right? So for confidence intervals, remember we had a number of samples that we want to run. We have the hypothesized value. We want to find out, what the upper and lower bounds of that value to be in order for us to accept our hypothesis. Okay. But we're going to solve this as a hypothesis testing problem. So we're going to run through the same 6 steps that we ran in the previous example. We're just going to do it for two-sided alternatives. Okay. Any questions on this? Okay. All right. So let's do the example. So now that we've kind of gone through the whole process, this is going to go a bit more quickly. Okay. Okay. So let's state our hypothesis first. So our hypothesis in this case is that X is going to be equal to 24, right? All right, next step is we're going to state our alternative, okay? Okay, so since we're doing a two-sided alternative, we're not using a greater than or less than sign. So the alternative in this case is the value of X is not equal to 24. So basically, we're going to reject our hypothesis if it's too great and if it's too little. Okay, next we have our significance level. And so the significance level in this case, we have to pick one. So let's just pick 5% just like before, okay? And so we convert this to a decimal. That means alpha is going to be 0.05. Okay. Okay. Step 4, right? So step 4, we're going to do twice because we're doing a two-sided alternative. So we're going to get a C1 for the left side and a C2 for the right side. Okay, so first thing, let's compute the degrees of freedom. So degrees of freedom, member, is n-1, or n in this case is 10, right? So we're going to assume that we're going to take 10 tests. So that means our degrees of freedom is 9. Okay. Okay. Now let's compute both C1s, both C's, so C1, C2. Okay. So let's do the left side first. Okay. So for the left side, we have F of C1 is equal to alpha, or 1/2 alpha, excuse me. Remember, that's the adjustment that we make for a two-sided alternative is we have the significance. Okay. So 1/2 alpha in this case is 0.025. Okay. So now we have both pieces of information that we need to compute our C. Okay. Now this one's a bit different, right? So since this one we know our variance before, yes, you. So since the variance is known, we're not going to use the t distribution anymore. We're going to use the Gaussian distribution. Now, I don't have this one tabulated for you, actually. So this is one that's in the textbook. So this is not one that I have a handout for. Although you can probably look it up online pretty easily as well. So for this value, you're just going to have to trust me a bit, but just know that I did verify this before, or technically I verified this in 2019 when I first taught this class. So in that case, the value for C1, if you use table A8 from the textbook, okay, the value for C1 under these circumstances for a normal distribution, Gaussian distribution, is minus 1.96. Okay, so let's repeat that same procedure for the right side, right? So for the right side, we're going to solve for C2. Okay, so f of C2 is equal to 1 minus 1/2 alpha, which is 0.975. Okay. Our degrees of freedom is still the same, so we still have 9 degrees of freedom. And so if we look up table A8, we get C2 is equal to positive 1.96. Okay. So you can see both our C values here have the same magnitude, which makes sense because the Gaussian distribution is symmetric, right? And so you have equal variance on both sides. T distribution is exactly the same. So if you want to be kind of efficient, you can just compute one side and just take the negative for the other side. Okay. Okay, so that's step 4 of our process. Step 5 is to run our experiment. Okay. And then compute the mean and standard deviation. Okay. But in this case, remember, for this particular example, we're not actually running our experiment. So we're actually going to skip step 5 because we want to find out what the mean should be. Okay. So for this one, and this is not usual, we're going to skip this one. Okay. And so we're going to go straight to step 6. Okay. So for step 6, we're going to use the same formula that we had before, except we're going to solve for something different. So we're not going to solve for t anymore, right? We're going to solve for x bar instead. Okay, so remember our formula from before was t is equal to x bar minus mu divided by, in this case, we have the known variance, and so this can be divided by sigma divided by square root of n. Okay. So remember, previously when we used this formula here, we solved for t, right? So we had our measured mean and we plugged that in here, solve for t, and compare that to c, okay? Now, we're going to solve for this instead, okay? And then for t, remember t and c have the same units, and so whatever we solve for c, we're going to plug in for that, okay? Okay. Solve this equation for x bar lower and x bar upper. Okay. All right. So again, plugging in C1 for t and solving for x bar. So this will be the lower x bar. Okay. So C1 is equal to x bar lower minus mu divided by sigma divided by square root of n. Okay. So let's solve for x bar lower here. So I'm going to multiply both sides by sigma divided by square root of n. So you have C1 sigma divided by square root of n. Okay. Plus mu is equal to x bar lower. Okay. So we plug everything in for this and we get X bar lower is equal to 22.14. And then we're going to repeat the same thing. So use the same formula, except instead of T on the instead of C1 on the left-hand side, we're going to use C2, and we're going to solve that equation for X bar upper. Okay, so C2 is equal to X bar upper minus mu divided by sigma divided by square root of n. Okay. So we solve for X bar upper, we get C2 sigma divided by square root of n plus mu. Okay. So we plug everything in, we get 25.86. Okay. All right, so that determines our lower and upper bound. So that means when we run our test, okay, and then we compute the value for X bar from that test, okay? So that means X bar must be in between, so it must be greater than 22.14 and less than 25.86, okay? Great. This is the criteria we must satisfy in order for us to accept our original hypothesis. All right. Any questions on this result here? Okay. All right. So one last thing that I want to note. So, just another application for these hypothesis testing. Okay. There is one more example. There's actually a couple more examples in the book or in the notes, right? So basically, I did the same example with 24. So I did this with the left-sided and right-sided alternatives, and so you can check those out in the notes. And I do have one more example with another structural problem where we're measuring the strength of a wire, and so definitely check those out if you want to see this process again. Okay. But I did want to talk about kind of one of the more common applications for this in engineering, which is in manufacturing quality control. Okay. So in the world of manufacturing, you're usually looking at the production and creation of lots of different parts, kind of you can imagine like an assembly line, right? Okay. So for such, large scale operations, right? It's impossible to make sure that, or it's impossible to guarantee that every single product that gets produced is going to be exactly the same. right? So through any kind of production process, especially processes that require multiple different steps, right? And so you can think of like food processing, something like that. This is something that's very, very common. I watched a very long video recently about canned sardines. That's one of my snacks that I really enjoy. I like eating fish from a can. So I watched a very long video in terms of the production process. It's fascinating. I think it's really cool. But something like that, it's impossible to really guarantee that every single can that you produce is going to be good, right? But you still want to sell this product to a customer, and so you want to make sure that your product, may not be at the tippy top, of quality. You want to make sure there's a bare minimum amount of quality so that you can sell your product to a customer and avoid them being upset at it, right? Okay. Okay. Why does everyone always have that reaction when I say I like canned fish? All my friends think it's so gross. I think it's like a very easy source of protein, and it's already cooked. You don't have to cook it. You just eat it. It's I see. I see. Okay. So quality control is actually a very fascinating field because on the one hand, I think the way that people think of quality control is that, you'll have quality engineers, you'll have quality kind of assurance people, QA people inspect every product and just to make sure that it satisfies that. So that certainly is part of the process as well. Okay. Okay. So that should be any part of any kind of QA, any kind of QA process, right? Anything that fails the inspection, you're going to throw it out. Okay. That's not really what we're talking about here, though, with hypothesis testing. Okay. Because what tends to happen for any kind of large kind of manufacturing process or assembly line process is that if you start to get a high percentage or a high volume of rejections, that could indicate that there may be something wrong with your process, right? So maybe a machine needs to be serviced. Maybe there's, maybe an infection that gets in, God forbid, or maybe there's a part that needs to be changed as well. Okay. And when you have such a complex process, it may be hard to really pinpoint where that problem is occurring if you're only testing for quality at the very end. Okay. Okay. So then what do you do in that scenario, right? So you can't, on the one hand, you can hire more QA people to do more inspections at several parts of your process, right? And sometimes that is part of the solution. Sometimes you hire more QA people inspect it at this point. That way you can kind of have more checkpoints in your manufacturing process. But a lot of times, that's not exactly practical. And so one way that certain companies that they do quality assurance and they do it kind of in a more efficient way is they measure certain metrics of the product as they go through certain checkpoints in the process, and this is fully automated. Okay. Okay. Now, by themselves, these measurements are, they're usually some kind of very base measurements. So they might be like temperature, they might be like, length, they might be a volume or an area, right? So by themselves, they may not indicate maybe something is wrong. And there's going to be variance in this, right? So there's going to be variance in these measurements. Okay. Right. And so the criteria or the way that these companies determine, when these measurements are used to reject product, right, is based on this theory of hypothesis testing, at least in a loose sense. Okay. All right, so think back to the last example that we just did, right? So in the last example, we determined, an upper and lower limit of the value of our variable for us to accept our product or variable, right? So the same thing can be done in manufacturing as well, right? So it's very common to have what's called a what's it called? A control line plot. And oftentimes that plot looks something like this. And so your plot will have an upper limit. Your plot will have a lower limit. And so some machine in the process is measuring kind of the value of that measured quantity. Okay. Okay. Right. And so as long as that measured quantity is within these limits, then the manufacturing process can continue. Okay. But if at any point where the measured value gets above the upper limit or below the lower limit, this is usually an indication that the deviance that we're experiencing is not normal, right? This is a little bit out of the ordinary. And so at this point, this is usually the parts of the process where, maybe the production line is stopped, maybe the machine is serviced, it's inspected, maybe some parts need to be kind of replaced, right? And so this is kind of one example of how this idea of hypothesis testing, accepting the fact that there is going to be some variance, there is going to be some deviance from your value. Not everything's going to be exactly what you expect it to be. But once that deviance gets beyond certain thresholds, that's when we can reject hypotheses. That's when we can kind of change our process or do something different. Okay. All right. Any questions on this before we wrap it up for today? Okay. All right. So that's all the time we have for today. I brought the exams again today. So if you didn't get a chance to pick up your exam on Tuesday, please come pick it up. This will probably be the last time I bring it to lecture. So if you don't pick it up today, it'll be in my office. Okay. All right. So thank you guys for coming today. Next week's our final week. And so Tuesday, we're going to learn about regression lines. And then Thursday, we're going to be reviewing for the final. Okay. So thank you guys for coming. Hope you guys have a good weekend. I'll see you guys next week.
For the homework, questions, the pre-response questions, asked to draw the left, right, and do double-sided limits. If I did it with the Gaussian curve, is that?
That's fine.
Okay.
That's more accurate. I would say that's a little.
Or what? So I was curious about except the variance. If the variance is known, that's the only time you can use the Gaussian, but that's a very rare occasion that you'd be using the Gaussian. So why?
So the t-distribution looks the same. And so when we determine that sample standard deviation, so the shape of the curve is always going to be the same. It's just how wide the peak is going to be. That's what we meant.
I see.
Yeah.
Okay. Just from the way you drew with the singular line, or it was on the notes. It's not a bell curve, so that's why I was wondering if there's a difference or.
Oh no, the t-distribution looks similar. It looks bell curve like. It's just the exact curvature is a bit different compared to.
Gotcha.
Yeah.
Thank you.
Yeah.
And then also, There's this Ukrainian store in Costa Mesa. called
Yeah.
Moscow Deli, and they have a ton of different sardines.
Oh.
My wife and I found one. It's called Riga Brats, and it's
Yeah.
in a glass container.
Yeah.
It's preserved in olive oil.
Oh,
If you like that.
oh, that sounds really good. I'll have to go try it.
Take care.
Yeah, you too.
Two things.
What's up?